Alright, so to start us off on the next few reactions we're going to look at, the first one we'll talk about is the halohydrin formation, right? So we're breaking it down, halo, halogen, hydrin, hydrate, right, water. And it's going to be very similar to the addition of halogen that we covered in the last video. So looking at this, right, we can already see kind of what's going to happen, right? So the alkene is going to end up forming that that cyclic halogen intermediate, and then water is going to come in and attack the site to get, in this case, chlorine to leave, and then we'll have OH as our other group stuck onto, in this case, our cyclohexane. So let's look at the mechanism for this. And again, it's going to be very similar to the addition of halogen mechanism we looked at in the last video. So in this case, right, we see not a bromonium ion, but a chloronium ion. And so that's going to look just like this. And again, because the chlorine can add either from the top or bottom, we'll say here that it, arbitrarily attacks from the top, but it can do either one, right? So now we have water add instead of the chlorine, right? And why does this happen? Because in this case, water is also our solvent, right? And there's a lot more water than chlorine in the reaction, right? Just as an FYI. So then water now will attack chlorine, okay? And it can attack from either position in this case, right? Because chlorine, there's no difference between these two sites. But to keep consistent with the product up top, we'll say it attacks here, okay? And so what we end up forming now is, right, in this case, we would have OH2 plus, right? And we'll go ahead and just skip the acid-base step, and we'll just say that, right, it deprotonated during the course of the reaction. And then we have chlorine, right? And again, this is an SN2-like mechanism. So we have that inversion of stereochemistry, right? You notice up here, right, we have not only the product listed, but we have the other ones as well, right? And so that forms through, right, two different ways. One, right, if the water attacked this other site, that would technically be this product, right, just kind of flipped upside down. But the other way we can form that is, right, by having, right, the chlorine not be on the wedge there in the chloronium ion, but have it on the dash. Right, and then we go through the same motions here, right, with the water attacking the this site, right, and we have, can't forget to have, right, the electrons pushed onto the chlorine at the end, and then we end up forming the opposite enantiomer, or rather the enantiomer, right? So we form this pair of enantiomers. And it is, as we can see, anti-addition, right? They are on opposite sides, they're not on the same side, okay? So again, very similar to the halogen addition, just with water instead of the opposing halogen, right? So this next addition here, we have catalytic hydrogenation, right? As you can kind of see, it looks very simple, right? We go from an alkene to an alkane, right? And we use these, or we do this reaction by a metal catalyst, right? So by metal catalyst, we can use nickel, platinum, palladium, sometimes it's called palladium on carbon, right? And this is kind of the most common one here, palladium and platinum. And so, right, as you can very clearly see, essentially the hydrogen just adds to the alkene, right? And this is a syn addition reaction where we end up forming those hydrogens, right? They add to the alkene at the same time, okay? So this is a syn addition. And the mechanism for this is a little bit more complicated, so I'm going to show you a quote-unquote mechanism to kind of explain what's happening. But again, this will definitely not be a mechanism you'll be required to know. But essentially, right, with a palladium catalyst, it's kind of like we have a surface of palladium, right? It's sort of this 3D structure of palladiums kind of all the way down, right? And with a lot of hydrogen, right, we kind of add a hydrogen atmosphere, right? And the hydrogen interacts with the metal. And so what we end up seeing is a lot of hydrogens on the surface of the palladium. And so when our alkene comes in, it interacts with the surface. And so what that kind of looks like is, and again, I'm not showing the whole story, but it's kind of giving you an idea. The alkene ends up adding or attacking the hydrogen, and then on the other site, right, because we'll get that carbocation, the hydride adds there. And that's how we kind of end up forming our cycloalkane from the cycloalkene. Right, essentially, hydrogen just interacts with the palladium and therefore allows the hydrogen then to interact in a meaningful way with the alkene. On its own, H2 is inert. You kind of need to use a metal catalyst in order to get that, again, syn addition of hydrogens to the alkene double bond. Okay, that's kind of all there is to it. So for the last mechanism here, or reaction rather, is something called epoxidation. Okay, so there's a lot going on the screen here, so I'll kind of guide you through things step by step. So epoxidation is essentially the formation of the cyclic oxygen here, right? And so this is a new functional group called an epoxide, right? It's a 3-membered ether, essentially, right? And these are typically very reactive. If you tried to make an epoxide with your model kit, it would be very tough, right? You'd see the bonds bending pretty heavily, right? And so that makes these sites here very ready to get attacked in an SN2-like fashion, okay? And we'll see examples of reactions with them later on down the road in the next video. But there's a couple ways we can form epoxides. The first one is right after doing a halohydrin formation, right, just like we covered just a few minutes ago. If we make this OH into a good nucleophile, right, using sodium hydroxide as a base, right, well, what we would end up seeing is the OH attacking our alkyl halide here, right, again as an O- after getting deprotonated, and we'd end up forming an epoxide, right, just a 3-membered cyclic ether. Another way we could do this, instead of going through the halohydrin route, is using a peroxide. And so these peroxide reactions, right, essentially, right, you can think of them as just making the epoxide, right, we lose one of the oxygens to make the epoxide from an alkene, right, and our product, or our side product here, is the carboxylic acid, right, from losing that oxygen, as you can see here. The mechanism for this is pretty interesting. Again, it'll be one of those mechanisms you don't need to know, but essentially, peroxides, like we've seen with Br2 and Cl2, can act like a nucleophile and electrophile, right? It'll both attack and get attacked throughout the course of the mechanism, right? So let's take a look at what that mechanism would look like. And so we'll use the following peroxide, and you'll see this one come up again a lot. So this peroxide here is called M-chlorobenzoic acid, or MCPBA for short. Okay, it's very, very common peroxide. So what ends up happening is when we react it with an alkene, the following happens. Where, again, the peroxide will act as a nucleophile and an electrophile. Right, it'll attack here, it'll attack the oxygen, and this will end up leaving. And then we end up getting the following peroxide, right? Here in this case, because, again, these aren't really chiral centers, right, doesn't matter, but the peroxide can add from the top or bottom. And this is technically, right, protonated, so we need to deprotonate it. And so we would end up doing that through, right, our formed O- here, right, the conjugate base of carboxylic acid, in order to get our final products. As listed above. Right? And so this is two ways to form epoxides, right? Just through this sort of SN2-like attack, or through using peroxide, right? Specifically MCPBA. And we'll look at some examples of where it'll matter whether these are chiral centers or not in our lecture examples. Okay, but again, it'll be a similar situation where through forming this epoxide, right, we'll get two different enantiomers, right, with oxygen at the top or bottom of the once alkene bond. So another thing that we can do with epoxides is do a acid catalyzed ring opening. Okay, so once we formed the epoxide, right, we can add some sort of acid, right, in this case, our hydronium ion. And so what ends up happening here, I'm going to redraw this to show you the arrow pushing. Right, the oxygen will act like a base, and will end up forming, kind of like we saw above, this positively charged epoxide intermediate. And so what can happen next is the water that formed, right, from deprotonating our hydronium ion will end up attacking that carbon site to have, right, alcohol as our group here. Right. And this is, of course, again, here it didn't matter. I'll put wedges to show you the end result. Is that this is technically, right, an anti-addition. Right, because it's an SN2 like attack. Right, SN2 like attack. And then for the final step, we just do some sort of deprotonation, which I'll indicate like that. Right, and so now we have, right, a sort of diol, right, two alcohols on the same molecule. Okay, so these are kind of all the things we can really do with epoxides in this case here. Like making them, and then this is one way that we can react them, right, in order to open them up. Okay, because again, epoxides are very reactive, so we'll see more examples of this down the road. So for the lecture examples, we'll go ahead and go through some of these and figure out, in some case, what the products are, or what reagents are needed to make certain products. Okay, and same here.